So the stream will be up. All right, so today we're going to talk about cameras and projections, okay? It's a little hard to talk about cameras and projections without actually talking about what a transform is, okay? So I'll give you guys a little bit of a matrix review on what a transform is. Anybody, what is a transform?
A 4x4 matrix.
What's up?
A 4x4 matrix. Position.
Position.
Size. Upright and left.
Right and left.
Upright and forward.
Yeah, upright and forward. Yeah, I guess it's a kind of a misfit. Anyone that came in for the matrix review is gonna kind of ruin it. So just gotta, if you already know it, I mean, just all right, help a brother out. All right, so transforms are where we need to start. We have to have some way to represent how do, like Zyron says. What you got for me? So which I say? So how do? Okay. Now we need to define a coordinate space. All right. So this coordinate space is going to be definable through a matrix, just like you said. Okay. So we're going to have some numbers represent that. If we were to try to represent world, how would we go about doing it? Okay. Well, the first thing that I'll say is like, all right, if we come in from Unity, a transform is this, right? That's a transform. They threw away my pizza box?
No, look. It's right there. In
Yeah.
Look, forward in that little Look right there in front of you, right
on the shelf.
I knew I was learning that one. So we're gonna need to define some type of coordinate space. This is a transform. True, false?
True.
I'm a duck. All right. This right here will represent some type of coordinate space. Okay. Notice some of the properties. Like this right here is really this. Okay. The line that's coming up this way, that's going to represent this coordinate plane. And then this line going this way is going to represent this coordinate plane. All right. Notice how it says coordinate plane, the plane. All right. These are planes. Okay. So these squares, these are the planes. How can we represent these planes with numbers? How many numbers would I need? There's a finite amount.
Depends on how big you want it to be. I'd say 4.
Four numbers to represent that entire box. That would be a good effort. Yes.
It would need a matrix.
You would need a matrix. This is where the matrices. This is where the matrices come in. Okay. So here we go. We're gonna define. I'll just throw up the identity matrix real quick and show you guys a little bit of something. All right. What do we want to call this line?
An axis.
Which axis? We'll call it X. What kind of X?
That's a word.
What kind of X?
Slope.
Positive.
Positive.
Okay.
This one?
Not positive. See negative.
You would, but not me. Okay. Z positive is going to be going outward, okay?
Like away.
It's very important that you know which direction you're dealing with, or if you're dealing with right-handed versus left-handed. All right. So this coordinate system, if you do like this, will give you the vector going out this way. All right. If you do this, not the same. Okay. All right. So that's the start of these matrices. All right. So if I were to say this was a unit vector, how would I represent it as a unit vector? How many numbers do I use?
2, 3, 1.
You said 2. That's actually a pretty good effort. But look, so we could start with 2. I don't know how we will start with 1. I don't got anything for that. But let's just say that we try to use these 2 numbers. It wouldn't really work out because of how we need to make everything uniform with one another. All right. So let's just say we're going to use 3 numbers to represent it. Then what would it be as a unit vector?
1, 0, 0.
It would be 1, 0, 0. Okay.
Oh.
Yeah, I guess.
So 1 0 0. And then what's this one?
0 1 0.
0 1 0. How about your boy?
0 0 1.
Okay. So what I have right here is a 3x3 matrix. Yes, 3x3 matrix. Okay. What are some consistencies about that matrix right there? It's all going down this way?
Looks like identity matrix.
It looks like an identity matrix, the identity matrix. Alright, so what can I do with this? So how would I use this to move this thing? Move it. I want to move it over here. This is where I want it. Could I use this to do that?
Yes.
How?
Add another. Yeah. Add
Well, no, man. What y'all just did? Y'all just defined orientation. Yeah, you can't move it.
Right.
You're gonna need another set of numbers to help represent that movement. Okay, that's the translation for it. So let's go ahead and bring it about and just say that this is gonna be 5 across. All right, 5 on what?
X.
How many on this one? Pretend that I didn't draw it incorrectly. 0 going up, and obviously it's not out here.
Right.
So now we got a non-n by n matrix. In computers, do we like it for it to be non-n by n, or even better, an n pot, power 2? So we'll just go ahead and make it power 2 by doing what? Say, look, see them things going down a diagonal like that. How about we just finish that off? The thing that we're using to finish it off is what's referred to as the homogeneous coordinate system, okay? Not just this, but this as a whole is the homogeneous coordinate system. We're making everything uniform with one another. We tacked off some extra information, and now we need to add, we'll say padding, okay, to get it to be correct, all right? So this 4x4 matrix is representing this, all right? What if I wanted to do this instead? How do?
Do thing.
How do? So look, if I have this right here, where I'm saying that I'm going to draw, I should have went with a triangle, I don't know why I did that, but a triangle, like this. How do I rotate it? How do I rotate that triangle? Basically, I need to get it to be over here. Even better, how would I go about doing just straight up this?
All the values change.
Okay, so now it's a little bit more clear. Maybe I'll just start off with that one. If I do this, what does this mean? Okay, so this right here is now what? If I were to rotate it
That's
around.
negative X.
Okay, so this top one is going to be, which way, Trent?
The top one?
Yeah, so if I rotate this whole thing around like this.
Y becomes X.
Yeah, there it is. Y'all heard that?
Yeah.
Y becomes which X? Which way is it facing?
X negative.
X negative. So you're gonna do this where it's like rip. So this is the Y positive.
Okay.
Okay, this is the X. This was the X positive. Your boy does not move. Okay? So I'm putting this to say like that's what these are rotating about. But in reality, this is the opposite of X, okay? This is now the Y. And this one has remained unchanged. Why does this one remain unchanged?
You rotate along that.
Because that's the one that you
Turn.
torqued on. Okay. So what would this look like whenever we were in here? Yeah, so this right here, all right, if you're talking about like these numbers where we said that we went ahead and we drew them out, this is the X, so X is now what?
0. Yeah.
The Y is now what? And this, then your boy?
Same.
Same. And then the rest of it, what's this?
5, 0.
No, that's that one.
0, 0.
0, 0, 0.
Well, if it would move over this way, it would be like, yeah, you would say like negative. But yeah, so this was
-5.
supposed, I can't draw on top of it. That would be a miss. Alright, so are we making some connection with this right here?
Yeah. Everything.
You're missing one.
You missing it.
I'm pretty sure I could go in Photoshop and pretend like that never happened. But or whatever editor. But so that's just like this visual representation, but how could I use some numbers and maybe feed into this thing to make it do this? What did I just do? I
Some
rotated
math.
it what?
Some math stuff.
Some what?
Some math stuff.
That's a good one. No, it is some math stuff. It would be some math stuff. It is not, it's not anything to get all bent out of shape about either, man.
Right.
I mean, I know it, so, like, all right, so if you're looking at this thing, what did I do? And when I'm in rotation, if I'm gonna count in numbers that are in distance, I'm gonna be like 1 meter, 2 meter, 3 meter. If I go to rotate, then I need to say I'm rotating one, what's the unit of measurement for rotation? Yes.
Radians.
Or, Trent, it can be radian. When you go to rotate, what you swiveling in your chair, man, like you are rotating how much? What's the number? It's like degree.
Yeah.
Okay, so it'd be a degree of rotation, all right? About the z-axis. Okay, so if we said this right here, then what? Oh, excuse me.
It's okay.
How many is that unit of measurement?
90
Degrees
degree, yes.
or how many radians?
45.
Huh?
45 radians.
Well, actually, it's not 90 degrees. Well, it's 90 degrees.
Yeah.
Yeah, it's 90 degrees. Yeah, it's pi over 2.
Okay.
Okay? Just point
Oh,
1 pi over 2. 3.14 divided by 2. Got it. 1.7. Okay. So yes, if you're looking at a circle that is it's a unit length everywhere,
Mhm.
this right here is 1.7. So it's 3.14 over 2. Okay.
All right.
I don't want to miss because fumble just regular math. So I need to use this somehow to get the new matrix, man. What two functions? Shit. Oh. So, I'll just go with it. What two functions do you know are like ebony and ivory? They go together real well.
Sine, cosine.
Ebony and ivory. All right. Yeah, sine and cosine, man. So if I were to try to represent this as cosine, what would it be? 1, 0, 0, right? So 1, 0, 0 is what this is. But if I'm trying to represent just the number 1 in terms of cosine, what would it be?
Sine 0.
So like, okay, if I got this right here, how can I represent this in terms of cosine, man? Does anyone know what cosine is? It's not like when you go get an apartment or a car. So what's cosine of 0? Cosine taking an argument of 0. Yes, it is 1. So this will be represented as cosine 0, comma 0, comma 0.
All right.
It's math, so I can't like
Mm-hmm. It is what it is.
Yeah, it is what it is. So cosine 0. Okay. So what if I just put that right here instead? So I'm gonna derive this like a matrix underneath this. Okay. Can everyone see it if I put it like underneath? Okay. So I'll just represent the x with a cosine 0, and then the y
Sine.
sine. So we'll start with that. We'll just say sine 0. All right. Now let's jump to this right here. Hello. Let's start with this one right here. So if I'm using cosine to represent this, I'm going to use sine to represent this. What is sine 0?
-1.
No, not that. Yeah, so sine 0, kickback 0.
Okay.
I thought it was negative sign. Okay.
All right. So what is the complement for it? Complement for sine? Cosine. All right, cosine. And once again, we left this unchanged. Questions so far? Okay, so cosine 0 is going to be 1. Okay, sine 0 will be 0. If this is going to be a representation of the y, which way did we go? We went this way.
Negative.
Yeah, so it would be negative, okay? There's more explanation to go with that, but I do have to do the cameras and projections. I'm kind of doing some favor here with these matrices. So this right here is referred to as the rotation matrix. All right. Whenever you rotate an object about, you need to figure out which way you want to, move it. In which I'm going to move this thing like this. All right. So when I have this, I can literally take this matrix, filling it in, and apply it to every point that makes up this shape. And then what do I get? This. If I gave this thing pi over 2, pi over 2, pi over 2, and pi over 2, what you're going to get is what, Reggie? 90 degrees of rotation. Thank you, Reggie. So 90 degrees of rotation. You go to do this on paper and you'll see it very fast, okay? Why? Because it's math and it can't be made up. These rules are very well defined, all right? Any questions with this? So this is a Z. This is a Z rotation. You're rotating about this axis, the Z axis,
Gotcha.
all right? In which you're only going to change the X and Y values. Yes?
What are the bottom 3 zeros used for?
This right here,
Yeah.
this is, like I said, it's like the padding for getting it to be homogeneous. We're about to cover it in the slides.
If you multiply any other matrix by the identity matrix, it means nothing changes, right?
Yes, correct. If you multiply by the identity matrix, nothing changes. Okay? So once again, you have an identity matrix, and then you define some points to help represent your geometry. If you wanted to move these things and rotate them about, well, you just multiply by however you're trying to change. This is called a matrix transformation. All right? This changes based off of the different rotations, okay? So whenever you're doing a Y rotation, that means that the Y axis will stay locked, okay? In which the X and Z will change respectively, and then the same for the other one, okay? All right, so we'll move on here. So we're going to be talking about cameras and projections. So virtual cameras and then the camera transforms. All right, we'll also talk about the journey that a vertex takes on its little way to actually get up on our screen. Should probably watch my grammar. It's okay. Fix it in post. So the journey of a vertex, where does it go? So whenever I started right here, okay, I'm just like defining things as we go. I'm just going to say, okay, well, I'm going to define this coordinate plane, and then I'm going to make some points with respect to it. This means that it's in the local space, all right? This is the local space here, the very first place I'm going to be making the model, okay, before it hits the video game.
Okay.
All right? From local space, we're going to be going to the world, okay, or the global space. So you're going to have, say like, you have the sun. We exist in the sun's space. And then we have the moon. The moon exists in the Earth's space. If the Earth rotates, the moon rotates. Okay? The sun doesn't care. If the sun rotates, the Earth and moon rotate. If the Earth rotates, Mars doesn't care because Mars is not within our space, our coordinate plane, okay? Okay. So, that's just a little bit of a refresher on what the global space is. Then we're going to talk about the view space. The view space is what we're actually going to be encapsulating within a volume. All right? So the camera, exactly. And then from the camera, we are going to be going to the window. All right? The window space or the clip space where we determine what's going to sit inside that window. All right? Once you transform from clip space, you're going to be applying... The clip space is, it's something new actually that that AI introduced. But the view space and then the clip space, you need to determine what's in the view of the camera. All right.
Projection.
Yeah. Well, no, not yet. Not yet.
Okay.
The window space is the screen space. Okay.
Yeah.
Clip space is like what is not in the actual volume of how a camera's seeing. Like I
Or
cannot
everything else.
cannot see Reggie.
Right.
I can't see him, okay, because he's not within my frustum, my viewing angle. All right. So that's what they mean by the clip space, and then we are going to apply some type of projection to whatever's actually within the volume of the camera, whether it be orthographic, perspective, or if they have some other weird type of projection, like in the fun houses, like whenever that's actually pretty good. I'm gonna get back on that. After you apply this projection, which will either skew or flatten your models, then you get it up on the screen in which it goes into screen space. Okay. Yeah. So just a little thing about the fun house. Whenever you go to one of those mirrors and they make you look fat, like that thing didn't touch you. It never looked at you. It just warped how you are perceived.
Right.
Okay. So, all right. So we'll talk about virtual cameras. The GPU has no concept of a camera, man. Like at all. There is no camera. You cannot go find by tag main camera. Like there's no, like where I go like get a pointer to the main camera find by tag. Like that's not a thing. Okay. There is no object moving around in virtual space that actually displays your scene for you, man. All right. The Futurama quote is, don't remember it. Okay, so it's I don't remember it like exactly how it says. Like the engine doesn't move around the world. The world is your oyster.
Yeah.
So
I got it.
I'm gonna remember that, man. And you know what?
You gonna look it up?
I'm just gonna throw it out there. Futurama quote. Yeah, I should probably watch my own stuff. Futurama quote engines world. Okay, so that's a miss. All right, that is not a good Google search for it. So here's the whole idea behind it, without Bender messing everything up for us. So it's easier to take everything that is defined within the world and then transform it versus what would it even mean to actually like move an object around.
Right.
Okay, so that's what we're doing whenever we say, okay, well here's the world. What I'm going to do to this whenever I rotate it about is I'm just going to manipulate every single object within that world by manipulating the actual world. Does that make sense?
Yes.
Okay, sweet. All right. So the GPU will display any geometry that is positioned within the clip space. So typically an area in the range -1 to 1 and an axis centered at 0, 0. Any geometry not in this space, it just won't appear. Yes, that's basically like what we're looking at. So in computer graphics, we create virtual cameras. So whenever you're thinking in terms of a camera and then you see picture in picture, like how does that even work, right? You're defining what a camera is, and then you just need to define what is inside of the camera, if that makes sense. Okay, whenever we get to the render target section of OpenGL, you guys will see pretty easy about it. So let me get my window open. Okay, so the job of the camera is to mathematically transform a 3D or 2D scene to fit within clip space, even if the geometry is positioned way off in the distance. Yes. In essence, we move the world around us when we render computer graphics. I should have just tried to do the winging it after I read all of that. We move the entire world around us, man. All right? So we define everything. Any questions? All right. So a virtual camera. So we typically create 2 matrix transforms to represent a virtual camera and 1 transform for every single 3D object in the scene. This is important. All right? This is very important. The very first matrix that we're going to be touching will be the world global model. All right? So you're going to have the world matrix, global matrix, and then the model matrix. The model matrix is the matrix that will represent how the points are set up. Okay? You're going to hear a lot of model view projection within the next couple of weeks over and over and over again, because we go model, matrix, all right? So how does that model get changed? And then we're going to have the view matrix, which is going to be the camera. And then we're going to have the projection matrix, which will define how we transform everything to be appropriate on the screen, okay? So the World Global Model Transform is to represent where a 3D object is in the scene. If you want to move an object in the scene, okay, then you're going to manipulate its matrix at that. Get it behind the head at that point before it touches the view matrix. All right. The view is a transform that represents the inverse of the camera's world transform that is used to transform the scene as if the camera is at the center of the world. All right. Where my glasses holder at, man? Nope. Well, Zara, I guess that's a miss. Okay, so basically what happens is that you have objects that exist on a plane. Come sort. Alright, so you have your world defined. You go get this model out and then put it right here. Okay? You did need to invent a camera in which we're going to say that the camera's matrix would be centered at the world.
Alright.
Okay? The camera then needs to look back at the world. Alright? So then it gets inverted.
Okay.
Alright? Does that make sense? If you want to put this within the camera's view, if the camera were right here, then this would need to get applied its inverse to move it in front of the camera. Okay? Are we on the same page?
What do you mean inverse?
What I mean by inverse is that we're going to state that we have a camera that is going to be located at a position, okay? And then whenever we invert it, it means we'll be looking at it. If I do not invert this, I'm not looking right at it. If two objects are centered at the world position right here, and then I move them, if I leave the model, so this is the model, they're both at the world, okay? And then I don't know if this is a good shape to go about doing it, but
That's the camera.
yeah, I'm trying to come up with some with the way that the camera's set up. So you have this right here. This is the camera. They're both just sitting here.
Yeah.
If I move the camera back, they're both facing the same way.
Can't see.
Yeah, if they're facing the same way, there's no way you could look at another person, man. Pole to pole. Like there's
Right.
no way. So you need to rotate it about or invert it. Whenever you invert it,
Yeah.
it's going to be looking right at it. Okay. This inverse matrix that you get, okay, is applied to the model. All right. So whenever we talk about the projection transform, I have this, and I know that this is looking back. Okay, so I'll pull it back and then I turn it around and now I'm looking at it. This is just a square. So that's going to mean that I'm just looking at another object on a flat surface. What does it mean for you to have depth whenever you're looking at things? Why do I know that Dylan's behind you, man? Seemed like some important information to know. He's like out to get that monies. Why do I know that? Why do I know that Max is behind Donray?
Oh yeah, Z value. Well,
Yeah, his Z value.
yeah.
Not so much though.
How do you if you can see him?
If I flatten this image out, how much space does Donray take up in my field of view? No, if I flatten this out, how much space does Donray take up? He takes up more space than Max. He fills
Yeah.
my view volume with more of Donray data.
Explosive.
Yeah. So, if we were to make that assumption, if this would flatten, they would be taking up roughly the same space. Like, there's no way to determine if he's behind him or not, okay? You would have to leave it to your GL enable depth buffer to help you out with that, because one would draw over the other. It's a flat surface, okay? Whenever we actually do perspective view, so everybody do me a solid and put your arms out until you cannot see your thumbs. So if you did like this and then do this until you can't see your thumbs. You can see, look straight and then do this and then stop when you can't see your thumbs. You ain't a fish. You can see your thumbs?
Still, yeah.
Hey, Dylan, put some fingers up next to his left thumb.
Yeah.
How many
Don't
fingers he
look,
got
don't
up? How
look.
many fingers he got up right now?
I don't know.
Yeah, you don't know, man. Move your arms in. All right. So my point is this: you can't see it, dude. Look,
Yeah.
I can see my thumbs. All right, I can see them. Not, I can see them. Look at this shape. So this shape goes like this. It's like a cut-off pyramid. All right. This is called a frustum. This is a view frustum. All right. So whenever we have this shape, if we could figure out a way to represent this shape and apply it to every single object in the scene, they're going to take on that shape. All right. When they take on that shape, they're going to shear differently because they're going to take up different volume of that shape. All right. So the act of that shearing is what is actually giving us perspective view projection. All right. So whenever you go to, oh look, I didn't give this example to you guys, all of you. The trick of the eyes, which one is taking up more space? The bowling ball or the golf ball? And then it's obvious, like, oh man, this is trying to get me, right? But the golf ball is literally like this big, but it's like,
Yeah.
okay? And then the other object is like very far away, but it's huge, and it looks like it's in front. So it's really just because it takes up more volume. All right, so let's talk about the journey of a vertex. Any questions about that?
About
Perspective view everything. Model projection, view projection, and then perspective view projection.
What projection were you talking about just now? Like
That is the perspective view projection. Okay, what is it called if it were square?
like this is like a box.
If it were just a box?
But what is that projection called?
That is called orthographic projection.
Right.
Okay?
We don't use that when we do this.
Hell no.
No.
The reason why is because you don't need to do it. All right?
Okay.
Orthographic view projection is a matrix that literally looks like this. All right. So if we were to go ahead and just define a homogeneous matrix from Soy, it's going to give you something along the lines of, even better, dude. If I go to do this, what are the different properties that I have of a square? Well, let's think in terms of the connecting pieces, man. You have a length and a width?
Yeah.
All right, so you have length and width. Well, whenever we're talking about a camera, we're going to have 4 properties. The width, the height, yeah, the far clip plane, and the near clip plane. Okay? So once you have width, height, you're going to say you have a near clip plane and a far clip plane. And then you figure out a way to represent this in here, and it's actually very simple, okay? If you go to do the math for it. So it ends up being like 2 over width, 2 over height. And I think it's like near clip over far clip for the Z. Something like that, all right? That matrix will get you, once you transform all the objects to it, in an orthographic view, okay? Whenever we talk about the perspective view matrix, you start to diddle up in there.
Yeah.
So it's outside the scope of my explanation, okay?
Whatever's in the box is what's being seen.
Exactly. Yeah, that's in the camera's volume.
Okay.
Exactly. Exactly. So we've now set the stage to discuss the transforms and then the actual pipeline further. Okay. So to render 3D points onto a screen of pixels, we are going to need to. This will be a test question. Exactly. Like, how do you go? What are the coordinate? What is the coordinate chain? You go from local space. All right. So you have local space vertices, and then you're going to put them in world space a world space. Oh. Okay. You know the struggle, Dylan. All right. You convert the local space vertices into a world space. All right. So if I were to say just what is a local space vertices, all right. Well, I'm going to just define just me. My hand is always to the right. If I have the root and it's 0, 0, 0, this thing is always going to be, for me, is going to be to the right.
Yeah.
Oh, look at my foot. So look, this is always positive to this. This will always be negative to this. This will be y positive to this. So those are local space coordinates. But what does that mean in terms of the world? All right. Well, if I'm looking at the world from my house, okay, then it's going to be B east. Okay.
Yeah.
Just wing that. But it's relative to the world itself.
Yeah.
So then we figure out. So we go from local space vertices to the world space. Then we're going to say, okay, well, we go world space to the actual view space. So now that I've defined me to be at work, okay, I'm relative to my home. Then I want to say, okay, well, now we're going to bring in a camera to define what is actually in the actual view, okay? Where this room, So say is the view. You can see me, all right? I exist because you can see me, right? But the kids in the other room, they don't see me. I'm not within the volume of the, you know, this room,
Right.
okay, to them. So this is where, like, I have no real world representation of it. Like, you have to go from a view space into a clip space. The clip space is going to be a normalization process, all right?
Rasterization.
Well, remember, it has to go from 0 to 1. I think it's 0. It's 0 to 1. And 0 to 1 here. Let me see what this. Yes, there we go. So we have a value. Oh man, there's a lot of them on the board. So let me get some of this out of here. So -1, 1, -1, 1 going up this way, and then that's how they run it here. So the clip space is how we are going to define things to lie within some normalized coordinate system. And then what we do is say, okay, this is the clip space. Now I need to get it out into the actual window space, all right, or the screen space, because everything is defined to be uniformly with one another, all right? Sweet. The engines don't move the ship at all. The ship stays where it is, and the engines move the universe around it. So take that, I'll print that at the beginning. So we convert the clip space vertices into screen space pixels. So this is the clip space. The screen space is going to be defined like this, because obviously so we go from this to this, okay? And that's where OpenGL comes in. OpenGL is going to do that for us. And every single one of these transformations are done with matrices, okay? All right, so here's a pretty good diagram of exactly what is happening. So you go from the local, and then you're gonna have the model matrix. Then you're gonna say, okay, well, I'm going to transform that into the world space vertices, and then the view matrix. Then now you have view space vertices, and then you have the projection matrix. And then you're going to get into the clip space vertices. The roster step, or the step where we actually color the pixels on the screen, is handled by OpenGL, or the GPU. Okay, so, yeah, they really beat this to death. So, and they should. So vertices start their journey towards pixeldom in local space. So you're going to hear artists, maybe not artists say, but I mean, when they're going to develop it in Maya, they don't really care if that thing is sitting in a pool. Like if they're modeling a character out and he's like, you know, laying back in a you know, a cot or something like that, like what Zyron is, like they don't care what it's going to look like in the game, you know. So they model it however it is, and then they expect for you to do you know, whatever it is you want to do with it. All of their positions are stored relative to their own unique central origin. That's exactly what I explained with this. Okay. The reasons for this are numerous. So mesh data for different assets are created and loaded separately. Yes, mesh data for different assets are created and loaded separately. I'm pretty sure you're aware of that, Jeremy. You're not going to use the same verts that you have for like every model. Like, what if you only had a pool of verts you could use? Like you ever open, whenever you were in Maya and you needed to make multiple objects, how many times did you ever just leave one scene open, model it, and have it like, oh man, I don't want to make another project. Just make a toilet or something like way off in the distance. Never? I do it all the time. So, but you could, like, so what would happen is that those would be defined, to, those two things would be relative to one another. So what happens is that if you model a bunch of things in an environment like that, and it's just looks like this big mashup of, or buffet of models and whatnot, you would, whenever you go to export it, you need to make sure that you bring it back to the origin. How many of you in your projects, whenever you were in Unity, imported an FBX and it just was like all, it was all messed up, like the scaling was incorrect, you know, it was maybe moved to the right a little bit.
That during the game jam.
No, yes, exact. That's it. Yeah, whenever he was with the games, we got some stuff from artists where they were like one unit off to the right, and then their rotation was messed up. So when he brought it into Unity, everybody was just doing a lot of unaccountable things. So, anyways, it allows for multiple copies of the same mesh used throughout the scene. This is also important because we're buffering our mesh data onto the graphics card. We don't touch it. We just put it on the graphics card and go about our business.
That would be the VBO.
Okay, so it allows for multiple copies of the same mesh used throughout the scene, just with different matrices defining their position, rotation, scale within a scene. Yes. So if I got like a model of a person, right? And my boss comes up to me and he's like, "Hey man, I just got this new feature request. I want to have little people now. So do you have a panic attack about it?" No, you don't. What do? You multiply matrix against them.
Before you get to the view.
Yes, before you get to the view, you just apply a matrix to them. You already have the data.
Scale.
You have all the data that makes up a midget human. Tried to be politically correct and missed. So, all right. So world space coordinates. We'll talk about it. So that was the local space coordinates. Now, in order to project our points onto the viewing plane, we need to figure out where all the vertices are in relation to the camera. Okay. All model vertices are currently in a local space, but we need them in the same coordinate space as the camera. So you must do this. You need to define a matrix with the rotation, scale, and translation of the model as a whole in world space or global space. This is called the world transform or the model transform. This is model transform. The pizza box is the model transform. Okay? Because I am defining this square that I drew in here with respect to this coordinate system, all right?
Position, a size, and a rotation.
What's up?
You said a position, a size, and a rotation.
Yes, position, size, rotation, or translation, rotation, scale. Okay? So we transform each of the local space vertex coordinates into world space by multiplying by this transform. So since the camera's position is also stored in the world space, this means we now have our points in the same coordinate space as the camera. Yes? Yes, because the camera is defined with respect to the same matrix system. It's like the Earth and Mars are within the Sun's matrix or transform. So the model matrix and then the local space is going to give you the world space, which is this right here. Like whenever we had the very first transform representation, or for those vertices, whenever we wanted to move it to the right, it was a new matrix that was just the identity, but then the very right column had 5001. That, with this, makes the model matrix, okay? In world space.
You do it for every model that you see.
Yes, you do it for every single one of them. When you go to write the code for it, you'll be very intimate with this concept. So the triangles of the mesh are not yet relative to the camera, which is why is how we need them. We need to transform them to view space relative to the camera, as if the camera was the center of the world, so that they can end up in the clip space. Like I've done this explanation already with the box and whatnot. Okay, you take the camera and then you put it in the world and you invert it and flip it. All right. So then, if you multiply each world space vertex by the inverse of the camera's world transform, it means the world space vertices are not oriented around the camera. Yes. Questions? Does anyone know how to ask a question right now? Nope.
No.
Make it stab. So we now have all vertices in the view space. Okay. They're transformed as if the camera is at the origin.
What do you mean by when it says the camera is at the origin?
So the origin is going to be defined to be
The camera?
the identity. Yeah, so like whenever you say the origin, like you're going to say, okay, well, like you have your world. You need to bring your camera to the middle of your world. What is the middle of your world? You could define it. I would set it to the identity. So you bring it to the what is you have your model, okay, and then your model is represented, say, like this.
Yeah.
All right. If he's way out here like this, I'm gonna make a camera that's gonna do right here. Okay, so I'm gonna bring my camera to the center. All right. Then we're gonna back the camera up, and then flip it.
Maybe rotate him a little bit.
Right. So that means that's how you bring the camera to the actual world, the center of the world. That's what that means. And then you need to take him and then bring him here. Okay. On multiplying these two matrices together, this is gonna bring him here. All right. This will put him with respect to these coordinate systems. All right. It's a good one. All right. We now need to transform all the visible geometry to fit within clip space. So once again, it goes from this right here to being something like this right here. But now we need to take them and then put them actually into some clip space. The clip space is how we normalize everything down. So we're going to put it between -1 and 1 values.
Okay.
So you take every single piece of every point that you have that makes up your geometry, and then you basically shrink it up. Okay? So when you shrink it up into the clip space, you're then going to get the bigger window space. Okay? So you have everything shrunken down together, then they're all within this one clip space, and now you can actually apply your projection transform once they're all uniform. So fit within a cube with dimensions -1 and 1 in all axes. To do this, we need a projection transform. So the projection transforms, I'll go ahead and zoom in on this a little bit so you can see. It doesn't like that very much. Hopefully you guys can see this. This is exactly what's happening, all right? You see the near clip plane, and you see everything that's within the volume. You see the far clip plane. Those things are outside of the box. So they are not going to be within the view space, okay? What it's trying to show you between the perspective view projection and the orthographic projection is that one of them looks like definitely behind the other one. You can see that, hopefully. Whereas the other one is just they're flattened right on top of each other. If it wasn't for the shadows, you wouldn't be able to tell at all.
Oh, it's showing perspective and orthographic
Mhm.
project. Okay.
Yep.
I thought it was showing the transformation. There's two separate things.
Which transformation?
Like whenever you say you go from view space to projection space.
Well, whenever you go from so you have the view space, and then you're going to move into the projection space, right?
Mm-hmm.
So the view space is defined to be the balls looking like they're in the center of the world, okay, where you have the camera, all right? Then you're going to apply to that the projection. How do you want these things to be sheared and whatnot?
Gotcha.
All right.
So how we're looking at it.
Perspective, depth, and orthographic depth.
Yeah, exactly. Orthographic is just a flat image, all right? You have no concept of depth based off of the volume that these things take up. Because of that shape, I could beat it to death in a one-on-one. But I've been going over and over like.
I thought you showed us that 2D, orthographic, you can actually see depth by coloration.
You can. Because everything is projected out into a two-dimensional plane. Like you're saying that if you were to be an orthographic view, just with regular orthographic view where the objects themselves are living, right? And then you just apply orthographic projection to it, it would be very difficult to tell if what is behind one another, okay? If there's no color. But once again, look at the shadows, man.
Right.
The shadows will tell you. Like you can see which one's behind the other one because guess what? The shadow for the one that's sitting like right here won't show up because the guy is taking it up. But your eye and your brain's making that assumption.
Yeah.
It just does it automatically.
Trick.
Yeah, it's just a trick. Okay. We get more in depth with it whenever we get to the lighting portion of OpenGL. Okay, so orthographic transforms, they have no field of view or aspect ratio, and they simply just resize a rectangular space to fit the clip space cube. It is, yes. Whatever the dimensions of your or however you define your orthographic view, it literally just takes the clip space and goes, beep.
Okay.
That's it. All right. So some more on orthographic projections. An orthographic projection matrix is the simplest to create. It behaves like a camera, just with tunnel vision. So no perspective for depth is possible. So back to what Don Ray was saying. How many of you have ever like seen those sidewalk art? It looks like somebody's like falling into it. Like you just look at it and go, nope. That looks like a lot to try to process. Yeah, it's like a lot. It's just on a sidewalk, on a 2D plane. But they know for a fact that you're going to, if you look at it from a very specific angle or viewpoint, then they can play tricks with you, okay? So, I'm going to leave this up to you guys here. You can read this. Like, we have this on the board. So here's the matrix, man. This is the matrix for orthographic projection. So the x value is 2, and then you have the following. So we're going to define a box. This box will be defined as such. Left and right. Okay? Top, the bottom. Near and far. So you need more. I guess you could just say that this is like this distance out right here would also be the. You guys, do you see it? All right, so the left, right, and then you have the near and the far, and then you have top and bottom. Okay.
Encapsulating.
Yeah. So you're defining a volume. So how would you go about defining that volume? I can write it on the board, but you can see it up here as well. The x value is just 2 over the right and the left. Right minus 2 over right minus left. Okay. The y value is going to be 2 divided by the top minus the bottom. Okay. The z value will be negative 2 divided by the far minus near. Negative 2 because push it out.
Right.
Okay. And then the translation matrix, I got nothing. That's a whole lot going on right there, man.
What?
Maybe Max, you got something for the top? That right, the translation part of that matrix?
Oh, wow.
Yeah, I think I would have to like kind of figure out what's going on right there. Right plus left.
Minus.
Yeah. If you just chug in a bunch of numbers, you could literally like do graphics by hand on paper, man.
Yeah.
Zarin, you can go. We'll get him up in like we gotta do that. All right, so orthographic projection. Now you're ready? Because I'm assuming perspective projection is gonna be next.
Yeah.
Okay, so we'll talk about the perspective frustum. A perspective projection uses a field of view and an aspect ratio to distort a frustum shape to fit the clip space cube. We basically need to make this. All right. So the field of view is usually specified as a vertical FOV in radians, typically pi over 4 or 45 degrees. All right. So something like this. This. How do I do that with a matrix? Oh, they holding on to it. They holding on to it. This is a pretty good picture. This is actually if you look up rotation matrices and then it says Introduction to OpenGL3, they show you this picture. So, as mentioned before, the perspective matrix distorts the space to fit the clip size. So, whenever all of those boxes are sitting together, okay? They're sitting within this clip space, but then we're going to have the camera set at a certain point, okay? And we need to take this, all right, and make it into the clip space. So what happens to everything if I transform it into clip space? Well, everything, like clip space needs to be a square, okay? So now you see all of the objects are manipulated to fit that shape. So you're basically applying that shape to each individual object, all right? And then that square is going to be put up on the screen itself.
And these changes have the objects that aren't in the view of the camera even? Okay.
Every single thing gets applied, yes.
Okay.
Everything. Everything. We change the entire world to match our needs. Okay?
Like our eyes, do we see like our field of view? Is it like a pyramid shape like that, or is it more of a conical shape? What was the question?
It's kind of hard to tell now I think about that.
Well, the way that an eyeball works is because light refracts.
Yeah.
Like, this is the way that I see it, man.
We see upside down.
You can see how far.
Pending variable.
Depends on a variable. Yeah, it's 2020.
Yeah.
Yeah, fair enough. Assuming you can see infinitely, if you think about the way that a camera itself works, like it's going to take a snapshot of whatever is in front of it. Okay, so if you adjust the variables that determine like how it focuses, okay, it basically says that I'm going to make sure that I make this little piece take up more of the volume so it's more clear. Okay. So the way that we actually see, whenever we say we see in perspective view, is like we don't see flat. It's like I mean, his question is like, do we see like this, or do we see like this? And then I mean, it's obvious. The answer is like we see like this because we can make determinations of depth. Okay, like Dylan has an issue where he has a problem with depth perception. Yeah, so Dylan. Yeah, he does. You have a problem with depth perception?
Yes.
Yeah, so Dylan has an issue with depth perception, okay? And it's literally just like the variables that make up how he defines his volume are a little wiggly, okay? But we do not see in a cylinder. If we were to see in a cylinder, that means that every single object would be uniform with one another. So a cone, like...
Oh, yeah.
Sorry, this... So, a cone, like... Trying to see, like, whenever you're looking at videos, like, it has a line that goes straight out like this, right? But, like, it's still flat. Like, there's still some flatness to it, okay? If it were a cone, you would... The only thing that you would be able to see is just, like, a little dots. Like, you have to have a method of projection.
Because the near the far clip plane.
Yes, it's exactly like the eyes are working exactly how this thing is, but it could be like so small that it does look just like a cone.
Like a pin.
Which we're saying that you're talking about. Do we see like this, or do we see like this? Is that your question?
Kind of, but like I'm talking about more like on like the farther side, like the shape, like for us on a camera, it's shaped just like a pyramid.
No, I got it.
But
It is conical. No, it's like at this point right here. Does it have like a little
yeah,
oval at the end of it?
yeah.
It's
Yeah.
like you're looking through a traffic cone.
No, like fisheye.
Right.
Yeah. Well, I concede. I'm not exactly sure because I mean it's things that are inside of this view. They're blurry. They are not blurry whenever you're looking at things on the screen, right? If you're looking at it on the screen, the clarity at the bottom is just the same as the clarity that's at the top. But it's like whenever we're looking at things, you have like this blurry area right here where it starts to taper off. Okay.
So we kind of, our eyes are kind of rounded, the lenses are. So like whenever we're projecting out, from our optical nerve, it goes like that. Because it rounds out through the lens.
Right. Okay. Yeah. Like I said, I concede. Because I mean that like the limit of it is that yes, it represents this part. Whenever we go out into the far clip plane, no expert. I'm not entirely sure. I'm pretty sure Wikipedia knows though. And I'm gonna find out before the end of it.
See a corner, right?
Okay. I think. All right. So if we're going to be building a perspective projection, so to build a perspective projection, we need to calculate how the field of view scales the x and y axes, how the aspect ratio scales the how the field of view scales the x and y axes. So so you have the x and y axes like this. The field of view is going to make it smaller. Okay.
Right.
This line will be smaller if it's closer. If it's farther, it'll be
Yeah, like.
larger.
Yeah.
Okay, so we need to figure out how to do that. The aspect ratio scales the x-axes.
I get that.
So if it's 16 by 9, okay, your aspect ratio is going to have some contribution to this guy. Okay, so this and this will then come in like this based off of aspect ratio, so it's going to shrink in. All right. How the far and near clip planes scale the z-axes. Yeah.
Like,
Yeah.
in relation to one another.
Yeah, so basically, like the farther out they are, how do we actually scale anything that's in between them?
Right.
Okay, and then offset the transform along the z-axis so that it fits between the clip space coordinate ranges.
Right. I don't want to do that. I want to do it.
Okay, so
It's making me frustrated.
math. All right,
Math.
yeah. So this is like the start of it, and I encourage you to go watch the Cameras and Projections lecture from Australia. I'd love to see what they say about this as a software engineer. So we use a vertical field of view as radius to calculate the scale for the x and y axes in our transform.
For a model.
Oh man, I can't.
Yeah.
Okay, so like I could work all this out, but we would all be struggling.
It said it's going to show an example of orthographic when they're talking about field of view.
No. So look, dude, it goes like this. You have the y positive and then the z positive, right?
Okay, we're.
Okay.
Yeah. All
Your
right.
x is facing at you,
Okay.
so you're looking that way. It's just so you can visualize it.
And we're looking to the right.
Yeah. So you're like this. You're just turned right here.
Okay.
Okay. So y stays up, but now my forward vector is looking out this way. If you were to start to work this out, it's literally just, doing something along the lines of this. And then you're doing some calculations on these for these angles right here. Okay. And then you could get that, which is just what, like the slope. It's like a slope calculation.
It's a map.
So, yes, I mean it's math. So, let's see if you have the field of view divided by 2. So if you say you have 45 and then you divide that by 2, or let's say your field of view was, you can say pi because I would just roll right over.
The field of view is 45 degrees.
So field of view is 45 degrees,
Okay.
22.5.
right? What was that in radians?
45 degrees is pi over 4.
So pi over 4.
Okay.
So pi over 4 divided by 2. I said I wasn't going to do it, but.
Good.
So pi over 4 will give you 0.785.
Okay.
All right.
Below 1.
And then divide that by 2. You get 0.392. So pi over 4. Divide that by 2. This will give you 0.392. And then if you do tangent on this, you get 0.414. So this 0.414 is going to be a representation of this line, okay?
In relation to view space. We're talking about view space.
Yeah, let's get back on track because of my, yes. So, this is how you calculate, you deriving the matrix for the perspective view projection, where you're using field of view to help you scale the x and the y. That's, I mean, if we were to, so when we have the test, it would say like, what does field of view affect? Field of view affects x and y, okay? That would be it. So, aspect ratio The aspect ratio represents the dimension of the screen as a ratio between the width and the height. So width divided by height, commonly is something like 16 by 9. So incorporating the aspect ratio into the equation is an easy step. So since the field of view was a vertical FOV, we simply need to scale the x-axis of our matrix. We do this by first multiplying the tan result by the aspect ratio before the divide.
Matt. Nice.
Thank you. Back to programming.
Nice.
All right. So the perspective view matrix, like, okay, like we are going. Whenever you write your applications for the camera class, you cannot use GLM look at. You have to make it,
Okay.
and it's going to be that matrix. So that matrix is your boy whenever you're trying to get projections out. There is no GLM look at. You have to create the camera, and then you're going to need to like copy that over, and then plug those values into your matrix, and you'll be using that matrix and applying it at the end of everything else. Okay?
Easiest matrix I've seen on this slide.
What's up?
Easiest matrix I've seen this whole entire slide.
That's the easiest matrix?
Yeah, just one page.
Yeah, I mean, you should be up here then. That thing gives me anxiety. Really, it does. Like, I can't explain. I'm not a mathematician. So, combining the matrices, so we can multiply each matrix individually against vertices, or we could just concatenate them together.
Concatenate them together.
Yep.
You adding?
No, man.
Oh.
No. You will never see add.
Yeah.
Unless you're like adding just one number. Like we don't do matrix addition as much as we do the following.
PBM, isn't that the one you said that you switched the values from PBM to MVP? Or
Yeah, that's what I'm about to do.
Yeah.
No, I'm gonna go over that. Like,
Yeah, explain
so what
that.
is the bro term for whenever I'm trying to get this out? You said that you had a model matrix. Then you said you had a view matrix.
Right.
And now you're saying that you have a projection matrix.
Good to go.
So if I have this one, and then you do this, and then you do this, what's wrong with this max? So if I'm trying to derive a result from the actual final matrix, so this is like this dude, okay, sitting in some coordinate space. This right here is the dude sitting in the viewport.
Yeah.
This dude is this guy, like this, all jacked up. I don't like.
Some depth.
He's all sheared out. Like,
Close.
so you have that projection matrix. Those things. Whenever you're multiplying them, the model view projection matrix is done like this. Model view projection. Okay, this is an actual, like, when I say times.
It's a thing.
Projection times the view times the model.
Doesn't matter which order.
Oh, tremendously. Okay.
What goes
This
first?
but this is it.
It goes left to right. Projection times view.
The model view projection matrix is the projection times the view times the model.
That's what's in the
Yeah, but it's just me explaining it.
Oh, I'm sorry.
I mean, I'm explaining it. Yeah, so whenever you go to look up things, man, like they're gonna say the model matrix, the view matrix, the projection matrix. Like, whenever you want to manipulate this thing, what can I do if I have this right here and I want to move the model to the right? And I didn't know about shaders.
Yeah.
How would I move them to the right? Where would I put it?
Before I do that.
You put it on the end. Look. Erp.
Oh man.
Did I say translate?
Yeah, some translation.
Right.
So the model matrix is going to be some like mangling of like if you just have the model there, yeah, it's going to be just the model. But I mean, the model matrix can like have it be moved around. It's really the world matrix, remember? Which is an accumulation of matrices that make up translation, rotation, and scale. So translation, rotation, scale. If you go to do this, you need to make sure that you scale it, then rotate it, then translate it. Alright, so this right here makes up this, but then again, if you just want to say, hey model, I need you to just move over to the right a little bit, you just tag it on to the end. Questions? Yes?
The specific order of what gets multiplied first. Like it's left to right? Or does it start from the end and
No, it starts from the end.
goes?
It's right to left.
Okay. Okay. Yeah.
If it helps you out, like you can say it's I mean you can say that it's the projection view model like this. If that helps you out, so PVM is the projection view times model, but in reality it's the model matrix and view matrix, and like think about the chain. The chain went model to view to what?
Projection.
Projection.
Where you gonna implement it, that's how you write it out.
Exactly.
Okay.
So the model matrix is going to be all the way to the right, then you're going to have the view matrix, and then you're going to have the projection. Okay?
That clears that up.
And then we're almost to like OpenGL, because this is what's going to get sent up. Alright, this is with respect to your video game. Once you buffer out the vertex data, you're going to send per object this matrix, okay? Questions? It's just, we've already gone over, man. I've said it so many different times. So screen space. Up to this point, the entire pipeline has been screen independent. I'll bring it back. Whatever. From here on out, OpenGL handles the conversion from clip space to screen space for rasterization. Yes, this is right. Like, you remember whenever we said we need to determine whether or not it's going to be. Let me see here. Let me just read it. From here on out, OpenGL handles the conversion from the clip space to the screen space for the rasterization. Before anything, the geometry is checked to see if it's actually inside the clip space. Single primitives are checked, which are the pieces that make up a complex model. Yes. Single points are easy. If X, Y, and Z are all within -1 and 1, then it is rasterized. For a line, if both points are within -1 and 1, it is rasterized. If neither are, it is ignored.
This is the shader part. This is where it's plugged
Nah,
in.
man, this is like right whenever it gets out to the screen after the fragment shader.
Really?
Yeah, dude, so like this is in the vertex shader.
Okay.
You send this to the vertex shader, okay?
Alright.
So from the vertex shader, it's going to go out to the fragment shader, in which is going to say, okay, well, what color do you want to be fragment? Alright? So once we have our fragment and then we determine what color it's going to be, we need to do the rasterization step, which is to determine like which part of the pixels is going to be like colored on top of.
Yeah.
Alright? Yeah, I don't know. I'd have to review this, man. Like, you're not gonna need to know exactly like how this this is actually occurring. The most important part with respect to the actual camera, and I'm gonna give you the assignment before we leave here, is gonna be that matrix right there. All right. So up to this point, the entire pipeline has been screen independent. Yeah, we didn't care about which screen we had to put this on, right? So based on our transforms and clip space, we have 3 slides left. Ignore the dimensions of the screen. In clip space, ignore the dimensions of the screen. Orthographic projection didn't need to use the screen dimensions. It's just useful to use it for pixel accurate placement. Yes. Yeah, I mean, screen space is like what part, how much of the screen, like if you're not in full screen mode, like you need to get it out into the actual screen space for the window, okay? Yeah.
These slides are available.
Yeah, they're on Canvas. We've gone over rasterization, so just as a review, man, it's the pancake mixer. Rasterization is the final step that the GPU performs before the fragment shader takes over to color the pixels. Screen space vertex data is interpolated across the surface that the primitive fills in, and the interpolated data is sent to the fragment shader to calculate whichever color you want. Yeah. Man, really? Just one? That's it? In summary, slide 2 and 3. On the road from 3D position, the colored pixels are vertices. They start in the local space. I think this is literally just a copy of the other slide, but this is the most important thing. This whole lecture, I drug it out because I practiced it, believe it or not.
Right.
Is this. I practiced it on Humanity. It's this. Yeah. But I mean,
Any other math, right?
the math involved in this, like, there's a lot of math involved in this.
Oh, of course.
The idea, in summary for this lecture is just, you have your model, you need to get it into the camera, so you move it over. Another big point was the fact that you take the camera, move it to the world, back it up, and invert it, alright? And then from that point, you're going to apply a shape to that accumulation, alright? So what I just said is this part, model times the view.
Yeah.
Okay, or excuse me, view times model. The view times the model is whenever you get this. This accumulation would be the final result of what is happening to every single word.
Right.
Yeah, it's gonna be some practice. So, any questions?